So with tins, we can apply a couple of operations to them. We can clip them out, again, like a cookie cutter, clip the tin to match your study area. You can erase features, which deletes the break lines. You can exclude areas, or what happens to that when you erase the break lines from a DEM, then that area is excluded from further interpolation or volume calculations. You can replace areas, uh, which redefines it as being flat. So this is very useful for modifying your tin if you need to incorporate a lake or a really flat excavation area. It gives the same elevation value all across that facet. So it's essentially flat. So here's just a couple of things that we can do to modify them. Once you generate a raw tin, you're not necessarily done, and you have a little bit of flexibility if you need to further redefine it beyond using mass points and break lines. You can do these more powerful operations to further modify your data sets. So we're going to switch into another specialized data set here, the terrain data set. And these are based on tins. They're stored in geodatabases as feature classes. Um, they operate at multiple resolutions with pyramid layers like rasters do. The tin is derived on the fly from reference data points, from break lines and mass points. So, in this case, LIDAR data and break lines, lake boundaries are creating for us this particular visualization of terrain. And so, the interesting thing is that unlike a tin or a DEM, it's not storing the entire surface information in the data set. It's just storing samples of them, and then it's generating the tin in the computer memory as you interact with the data set. So it's a very interesting kind of a data set to use. It's not something that our workbook uses, but you should be aware of it. It's one that you may find useful for different applications in managing things at the landscape level. One of the things I should point out is that you can not only generate tins from DEMs, you can generate the other way around. You can go from a tin back to a raster. However, you should be aware, of course, which should be obvious, but I'll point it out, is that once you've created a triangulated irregular network from a DEM, you've modified that information. You can't go back to exactly the same information. You're going to be introducing some error if you go back from the TEM, create another raster of elevation from it. So if someone goes through a cycle of starting with a DEM, creating a tin, and then deciding, I deleted my DEM, I need to create another one, so I'm going to create a DEM from that, it's not going to be as good as the original. And if someone else says, well, I'm going to generate a tin from this new DEM, and they generate a tin, they're introducing more error. It's going to be uh, less of a correlation between the information in the tin and the actual landscape information that's out there on the real landscape. And it's going to be even further from the original DEM and so forth. So be careful if you decide to use these tools, and only create a DEM from a tin if you absolutely need to for any particular reason. I would strongly recommend that you only create tins from an original DEM and then leave it alone. Don't mess with it. Don't do the other tool. Don't go back and create another DEM and get into a cycle of doing those types of things. You're going to create lots and lots of error in your data sets. But here it is one of the functions that's available in ArcGIS. So I'm just pointing it out. And with the warning caveat, don't go back and forth between these. If you need to generate multiple tins, you generate multiple tins from the same original raster, and don't go the other way. So when a DEM gets sampled, not every cell location is used as a point to build the tin. There's a parameter called the Z tolerance. Z here refers to vertical elevation above mean sea level. So we use a Z tolerance to determine triangle sizes, which is basically going to be selecting the points that are created from the grid cells. How far away is it going to go to sample to find those in terms of elevation change in order to create a facet? So visually, over on the left, with a Z tolerance of 6 meters, in this particular example, we're generating 74,552 triangles. So Z tolerance means it's searching within a vertical distance of 6 meters given input raster cell values that are converted to points, which become points in the tin. In the middle, a Z tolerance of 20 meters produces 15,225 triangles. So we're increasing the search range, the Z tolerance. We're decreasing the number of triangles, which ultimately means that the resolution of the tin is coarser. Okay, and it doesn't represent the landscape as well as the Z tolerance of 6 meters. On the right, if we use a Z tolerance of 50 meters, we're only getting 4,424 triangles as the output. So this is an even coarser version of a landscape surface. All three of these derived from the same DEM, showing essentially Mount St. Helens after eruption. So after 1980, what does Mount St. Helens look like as a tin? The one on the far left with a Z tolerance of 6 meters gives us something that's much closer approximation to the actual landscape configuration than the ones in the middle and to the far right. And so that Z tolerance is a threshold that's very critical in not only the complexity of the tin itself, but how well it's going to model the landscape. So here, using that same example, let's look at Mount St. Helens as a DEM, creating tins off of it. Original DEM, 1.38 million cells. The Z tolerance of 6 meters generates 38,000 nodes. The Z tolerance of 20 meters generates 8,200 nodes, or connections between different edges that are the points. The Z tolerance of 50 meters, 2,700 nodes. So here, not just in that framework version, but what the tin actually looks like compared to the DEM, which is all just raster cells. The next one over with the Z tolerance of 6 meters, that's doing a really nice job of describing the landscape, visualizing the landscape of relief changes between the high points and the low points, between the mountain peaks and ridge to the incised canyons from the rivers that are flowing down it, and all the other topography that's there. To the right, with the Z tolerance of 20 meters, it's getting not blocky, it's getting triangularly, it's getting more facets are visible, it's rougher. It's not as fine as the one at 6 meters. So it's not doing as wonderful a job of depicting the landscape in detail. To the right, with the Z tolerance of 50 meters, it's even chunkier, and the facets are even larger. And so this is probably, the least accurate between representation between what the tin looks like and what the landscape configuration actually is. So your Z tolerance, the smaller it is, the more triangles you're going to wind up with, the more edges, the more nodes, the more fat, all of that stuff. But it's going to do a much better job of showing the terrain close to what it naturally looks like if you're viewing the landscape, in this case from a satellite overhead or from an airplane or anything like that. So again, Z tolerance very critical in how your tin output will function visually and be a visualization aid for whatever kind of analysis you're doing. So to compare these two things a little bit, DEMs and tins, DEMs are using a single resolution, the cell size itself, which doesn't vary across the landscape. It's a regular grid of the same size cell everywhere. Tins are composed of triangles that can vary quite a bit in size as those triangles are generated to try to model the shifting values of elevation, slope, and aspect. DEMs, as a regular grid, do not incorporate hard landscape features, whereas tins can include things like the break lines, polygons, and mass points that can be used to essentially chop up the tin and create other polygon features that better approximate the actual landscape, the actual hard features on the landscape. The DEM computation, fairly straightforward and easy. Tin computation is complex. That's a throwback to times when we had less capable computers. It's going to take a little while to do DEM and tin computations, I mean, no matter what, but with modern processors and RAM and hard drive speeds and capacities, there's really not that much of a huge difference between these two things. It comes down to what type of data you need for analysis or for visualization, which one seems to do the better job, and which one you prefer, or perhaps, given a particular project, which one you've been told to use. Okay, there's certain things you can do with DEMs. You can do a lot of analysis with DEMs. Tins, there's some things you can do with them, but for most practical purposes, they're a visualization technique. So now we switch gears again, and we're going to look at another way to depict terrain, and this is one that you're probably familiar with, the isopleth. You may not be familiar with that word, but another word you can use for that, if you break it down, iso equal pleth line, contours. So contour lines describing elevation change across space. So this is a vector data model depicting terrain. And so this is probably a review, but how contour lines or lines of equal elevation get calculated or created is based upon known point locations, so known elevations. Here we've got several different locations across space. The point locations are the number values. We're trying to figure out where to draw contour lines between the values. So you apply the equation over on the left, a placement equation, for the change in elevation values and the distance between them, and then you're placing the iso line on the map. So how these things work in practice is that an iso line, an isopleth, a contour line, is a line of equal elevation. Isopleth in general means line of equal value. How that works with elevation as an example is that every point on that line is that elevation. And there's an interval between the lines. In this case, it's a 10 unit interval. So it's going from, let's call it feet, from 30 feet to 40 feet to 50 feet. And that's the change in elevation values recorded by those lines on the landscape. And so if you combine a lot of these lines over a larger area, it's going to give you a visualization of what that terrain looks like in general. But you have to have those values on the lines, otherwise it doesn't make any sense. It's just a bunch of wavy lines drawn on a page or on a map that really have no meaning. So you really need to have the values with them in order for this thing to make a lot of sense. So here's a great example of a photo showing a particular location. Up on top, you see the camera location. Down on the bottom is the photo of that spot, and contour lines describing the landscape. So looking straight ahead, you see a cliff face. There's kind of a little promontory off to the right, and looks like kind of a mountain bulge or a hill way in the background. So looking at the top, we see contour lines that are being used with it. We don't know what the contour interval is, unfortunately. But if you can imagine, down by point A, it's relatively flat. And as you move towards the top of the diagram, you're climbing up that cliff face. And where the lines are closely spaced together, it's very, very steep. Where they're more spaced apart, it's flatter terrain, a more gradual slope. And so if you do a little bit of comparison there visually between the photo and what we're seeing on the contour map, you can see how the contours are describing the changes in relief, the vertical changes of elevation values, especially that cliff face and the mountain behind it showing up really nicely in that depiction of the contours. One of the things to note with contours as a form of depicting landscape, I should mention, is probably the rule of V's. And the rule of V's is that they're streams, when they are flowing or when water's flowing across the surface and erodes it, it will tend to erode it and form a V pattern. And so the V pattern, how we would normally draw that, visualize a letter V, and the bottom of the V, where the two lines come together at a point, on a contour map, that points uphill. As erosion carves away the material, it leaves behind a succession of V's that are describing a river channel or an erosion pathway. There's one that's really nicely described right there between points C and D on the contour map. You can match that up with what's missing there on the cliff face in the photograph, and you can see that really strong correlation between the contour lines forming a V that points uphill and the actual landscape configuration. Okay, so contours, it takes a little while to get used to them and how to read them, but if you get familiar with the how different landforms look in contour form, then looking at a topo map is just like reading a book for the landscape. It's really a neat skill to have, and an interesting way to depict landforms that has been around for a very long time, but we still use it today to help us understand landforms and landform change. So I've got a succession of different slides here really quickly and briefly to show this notion of DEM and contour. So DEM on the left, contours on the right, obviously. Showing, using our example of St. Helens again, we've got kind of that interesting DEM form. If you're used to what DEMs are and you're familiar with the color patterns that are applied to them, this is more of a traditional atlas coloration than it is in ArcGIS applied color ramp. But still, if you're familiar with reading atlases and traditional maps, then this makes sense. You look at it, you can see the formation of a mountain peak and the depression or hollow where the volcanic eruption blasted out the top of the mountain and the northern slope of the mountain. Over on the right is the contour depiction of the same thing. And again, remember the rule of V's, and the idea is that the more densely packed the contours are to each other, the swifter the elevation change, and the more distance between the contours, the more gradual the elevation change. which is doing a slightly better job of showing us the landscape probably than the DEM alone does. We're seeing faster transitions between slope changes on the contour map than we are on the DEM.